Hello, my name is Derek McKee, and I'm presenting the paper Preventing Kernel Hacks with HAKCs. This was a joint effort between me at Purdue University and my colleagues at MIT Lincoln Laboratory and EPFL. HAKCs enforces a least privilege policy on monolithic software, which is a widely used security technique that has been proven difficult to apply in system software. As motivation for this work, we analyzed the last 5 years of high-severity CVEs issued for the Linux kernel and determined what mitigation, if any, would have prevented the exploit. We found that most CVEs could have been mitigated had a least privilege policy been imposed. Memory safety was a close second mitigation, and interestingly, there was only a limited intersection of CVEs that would have been prevented if either mitigation was in place. Given its larger impact, we therefore opted to tackle the privilege separation problem, and the design we came up with is the HAKC system.
HAKC, which stands for Hardware-Assisted Kernel Compartmentalization, is an enforcement mechanism for any arbitrary compartmentalization policy. HAKC runs on bare metal without the need for any virtualization or security monitoring layer. To enforce the compartments, HAKC uses two new ARM extensions, Pointer Authentication Code, or PAC, and Memory Tagging Extensions, or MTE. PAC allows a user to specify a context with which a pointer will be signed, and the signature is stored in the upper 16 bits of the pointer. The original pointer can be retrieved if PAC is presented with the signed pointer and the context with which it was signed. MTE allows a region of memory to be tagged or colored with one of 16 colors, and allows the retrieval of the data color via a pointer.
The Linux kernel can be broadly divided into two parts, the core kernel and kernel modules. The core kernel is the image that gets loaded by the bootloader when starting the computer. However, in an effort to reduce the size of the core kernel image, some functionality is separated from the core kernel and is dynamically loaded when the functionality is needed. These dynamically loaded objects are collectively called kernel modules, and they are often used for device drivers, file systems, or protocol implementations. When a kernel module gets loaded by the kernel, however, it becomes indistinguishable from the core kernel code, and in monolithic software, like the Linux kernel, has full access to all kernel data. Kernel module code is often less vetted than core kernel code, but a kernel module bug is just as severe as a core kernel bug. HAKCs targets kernel modules for compartmentalization. To illustrate the type of bug HAKCs mitigates, consider this code, which is based on CVE 2016-4997. The code, which is part of a packet filtering mechanism, runs during error cleanup and can be used to decrement arbitrary kernel data. One of the members of struct entry is used to store an offset value, and if the offset is lower than offset max, the offset value is used to compute a pointer to an integer. That pointer is given to a callback function, and the underlying integer is decremented by 1 after the callback function returns. The bug is caused by a lack of a lower bound check in the first line. The offset member can be user-controlled, and the lack of a lower bound check means that the pointer can point to arbitrary kernel data by making offset be a large negative number. An attacker can be made root by repeatedly calling this function and making I point to their user ID. HAKCs works by reading a compartmentalization policy provided by the developer that combines related code and data into a structure called a click. A set of clicks is further bundled into another structure called a compartment. Each click is assigned a color unique to the compartment, but not globally unique. Additionally, The compartmentalization policy defines an access control policy for each click. In this case, the yellow click can access yellow, green, and black data, while green can only access its own data. If we repeat this for all the rest of the code we want to compartmentalize, we can end up in a layout like this. The two-level partitioning separating clicks and compartments allows HAKCs to safely reuse colors and optimizes for data locality for commonly used data. Finally, the compartmentalization policy dictates valid control flow transfers between compartments. In this case, the IPv6 compartment can transfer to the Bluetooth and packet filtering compartments, but cannot transfer control to the ext4 compartment. HAKCs enforces data ownership using PAK and MTE. All data must belong to exactly one click within a compartment, and any data accessed by a click must follow that click's data access policy. When control flow needs to exit the compartment, data ownership must be transferred to the target click before control can flow to that click. Data ownership transfer involves a recoloring of the data using MTE and a pointer reassigning with PAK using the target click, color, and compartment as the PAK context. When the target function returns, the data is recolored its original color and reassigned to restore data ownership to the original click. HAKCs enforces the data access policy within a compartment and performs compartment transfers by instrumenting code using an LOVM pass. In our example from earlier, HAKCs first checks that I is a valid pointer. Next, HAKCs adds a check to ensure that the function pointer is in the set of valid compartment transitions. The transfer process, which is written by the user, actually calls the color and signing functions to transfer the ownership of I to the yellow Bluetooth compartment, and back to the green IPv6 compartment when the function returns. The CVE that inspired this code would be mitigated with the data check on I, because the pointer signature would be invalid. HAKCs uses both MTE and PAK to check that data is validly accessible. Checking data with HAKCs starts with a signed pointer shown here, with the upper bits storing the signature. HAKCs first gets the color of the data, and then the color is compared with the click access control list. The result of the access control check is combined with the compartment identifier into a PAK context. The context and the signed pointer are given to the PAK authentication instruction, which results in a valid unsigned pointer that can be used for access. If the data color is not accessible per the access control list, or the data was signed with a different compartment identifier, the PAK authentication will result in an invalid pointer. To evaluate HAKCs, we wanted to measure the overhead induced by compartmentalization and whether users would notice when they are using a compartmentalized system. To that end, we compartmentalized the Linux IPv6 kernel module in one of the Linux packet filtering implementations. We measured the overhead induced when transferring various sized files using Apachebench when the IPv6 module was running alone, and with the packet filtering module running alongside. All experiments were performed using a Raspberry Pi 4, pictured here. As no hardware exists that implements PAK and MTE, the instructions were replaced with analogs. The details can be found in our paper. This chart plots the requests per second and transfer rate the compartmentalized IPv6 module achieved normalized to the uncompartmentalized kernel. The overhead ranges from 2% to 20%. The highest overhead comes when transferring the smallest file. This is because establishing a TCP connection involves a lot of HAKC checks, but once the session is established, transferring the file is relatively simple. Therefore, for small files, the TCP connection time dominates the full transfer time, while for larger files, that time is amortized. Repeating the same experiment with both the IPv6 and packet filtering active, we measure a linear overhead increase. However, we claim that this is a worst-case scenario, as both modules operate sequentially on the same data. To determine if a user would notice the use of a compartmentalized IPv6 module, we selected the top 50 Alexa websites that broadcast an IPv6 address, and measured the time difference from the uncompartmentalized kernel to render each page. The compartmentalized module took 1.19 seconds slower to render the web pages. However, the standard deviation was 4.34 seconds. Given that the standard deviation is more than 2 times the average, we conclude that users will not notice a difference browsing the internet using the compartmentalized module. The table lists the 5 websites with the highest and lowest standard deviations. Notice investing.com is a significant outlier in both load time delta and standard deviation. For that reason, we did not include it in our average load time measurement. In summary, HAKC utilizes a novel 2-level enforcement mechanism for compartmentalizing kernel code without virtualization. Enforcing a least privilege policy in system software has been difficult to implement. However, combining 2 new hardware features, HAK and MTE, makes enforcement of compartments a feasible task. HAKC imposes low overhead, yet provides strong protections for data and control flow. We have open sourced our implementation and it is available at the listed URL. Thank you very much.